Hello there, and welcome to the Sleepy Science Astro. I'm so glad you found your way here tonight. Maybe you've been looking up at the stars, wondering about the mysteries that unfold in the darkness above. Or maybe you just need a peaceful place to let your thoughts drift and your body settle into rest. Whatever brought you here, you're welcome. There's nothing you need to do now but breathe, relax, and let yourself float gently through the wonders of space. Tonight, we're going to explore some of the most beautiful and fascinating phenomena in the universe. Not with urgency or complexity, but slowly, softly, like watching clouds drift across a summer sky. We'll discover auroras on distant planets, stars that pulse like cosmic lighthouses, nebulae that glow in colors we can barely imagine, and quiet forces that shape galaxies across billions of years. Some facts may surprise you. Others will simply wash over you like a gentle wave, soothing and soft. And if you drift off before we finish, that's exactly as it should be. If these calm explorations bring you peace or spark your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let your shoulders drop, your breathing slow, and your mind grow quiet. Let's begin this gentle journey through the phenomena of space. The shimmering curtains of light we call auroras aren't unique to our planet. Jupiter, Saturn, Uranus, and Neptune all have their own versions, sometimes even more spectacular than ours. These celestial light shows occur when charged particles from the Sun collide with a planet's magnetic field and atmosphere, causing gases to glow in brilliant colors. On Jupiter, the auroras are so powerful they can be seen in ultraviolet and X-ray wavelengths, creating halos of light around the planet's poles that dwarf anything on Earth. Saturn's auroras pulse and flicker across its northern and southern skies, influenced by its powerful magnetic field and the solar wind. Even distant Uranus, tilted on its side, has auroras that twist and spiral in unusual patterns. These cosmic light displays remind us that Earth is not alone in hosting such beauty. Across the solar system, planets glow with their own silent, electric dances, painting the darkness with color and energy. When a massive star collapses, it can form a neutron star, an incredibly dense object just 20 kilometers across, but with more mass than our Sun. Some of these stellar remnants spin at astonishing speeds, rotating hundreds of times every second. These rapidly spinning neutron stars are called pulsars, and they emit beams of radiation from their magnetic poles like cosmic lighthouses. As the star rotates, these beams sweep across space, and if one crosses Earth, we detect regular pulses of light or radio waves. The fastest known pulsar spins 716 times per second, a rate almost impossible to comprehend. Despite their incredible speed, pulsars are remarkably precise, keeping time better than any clock humans have made. They're powered by the conservation of angular momentum from the original star's rotation, compressed into a tiny, dense sphere. In the quiet vastness of space, these ancient stellar cores tick away, spinning faster than thought, marking cosmic time with unwavering rhythm. The fact that we can see total solar eclipses from Earth is an extraordinary accident of celestial geometry. The Sun is about 400 times wider than the Moon, but it's also roughly 400 times farther away. This means that from our perspective, they appear almost exactly the same size in the sky. When the Moon passes directly between Earth and the Sun, it can perfectly cover the solar disk, revealing the Sun's ethereal corona. This precise alignment is temporary in cosmic terms. Millions of years ago, the Moon was closer and would have appeared larger, creating longer eclipses. Millions of years from now, as the Moon slowly drifts away from Earth, it will appear smaller, and total solar eclipses will no longer be possible. We live in a brief window of time when these perfect alignments occur, a fleeting cosmic gift. Other planets have moons, but none create the same stunning symmetry. It's a reminder that sometimes the universe arranges itself in ways that feel almost intentional, even though they're simply beautiful accidents of physics and time. Scattered throughout the galaxy are vast clouds of gas and dust called nebulae, glowing softly in the darkness like cosmic gardens. These clouds are where stars are born. When regions within a nebula become dense enough, gravity begins to pull the material together, creating pockets of increasing pressure and temperature. Over millions of years, these collapsing clouds heat up until nuclear fusion ignites in their cores and new stars begin to shine. The remaining gas and dust often form planets, moons, and asteroids around these young stars. Some nebulae glow with vibrant colors: red from hydrogen, blue from oxygen, green from other elements, illuminated by the light of newly formed stars within them. The Orion Nebula, visible even with small telescopes, is one such stellar nursery, filled with hundreds of young stars still emerging from their dusty cocoons. These nebulae are not just beautiful, they're essential, the cosmic wombs where starlight is kindled and planetary systems begin their long journeys through time. Despite their fearsome reputation, black holes don't act like cosmic vacuum cleaners pulling in everything around them. They follow the same rules of gravity as any other massive object. If our sun was suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now, no closer, no farther. The danger of a black hole lies only in getting too close to its event horizon, the boundary beyond which escape becomes impossible. Outside that boundary, gravity behaves normally. You could orbit a black hole safely, just as you could orbit a star. What makes black holes unique is their incredible density, so much mass compressed into such a small space that within the event horizon, not even light can escape. But at a distance, they're just gravitationally bound objects like planets or stars. They don't reach out and grab, they simply curve space around them. In the vastness of the galaxy, black holes drift quietly, influencing their surroundings with gravity, but not consuming everything in their path. For a few seconds or minutes, a gamma-ray burst can outshine entire galaxies, releasing more energy than the Sun will produce in its entire 10 billion-year lifetime. These are the most powerful electromagnetic events known to occur in the universe. Most gamma-ray bursts are thought to come from the collapse of massive stars into black holes, or from the collision of neutron stars. When such an event occurs, jets of particles are blasted out at nearly the speed of light, and if one of those jets points toward Earth, we detect a brief, intense flash of gamma rays. Fortunately, these bursts are rare and occur in distant galaxies far from our own. If one were to happen nearby and point in our direction, the radiation could be catastrophic. But across the universe, these brilliant flares mark the deaths of stars and the births of black holes, brief moments of almost unimaginable violence shining across billions of light years. They are nature's spotlights, sudden and blinding, illuminating the universe's most extreme moments. When massive objects like black holes or neutron stars spiral into each other, they create ripples in the very fabric of spacetime itself. These are gravitational waves, distortions that travel outward at the speed of light, stretching and squeezing space as they pass. Albert Einstein predicted their existence over a century ago, but they weren't directly detected until 2015, when the LIGO Observatory measured the faint tremor from two black holes merging over 1 billion light-years away. The waves were so subtle that they changed the length of LIGO's detectors by less than 1,000th the width of a proton. Yet they were real, carrying information about distant cosmic collisions. Gravitational waves let us observe events that produce no light, opening a new way to explore the universe. They are silent, invisible, and incredibly gentle by the time. They reach us but they represent some of the most violent moments in cosmic history. Space itself shivers when giants collide, and now we can feel those distant tremors. After a massive star explodes in a supernova, it doesn't simply disappear. The blast sends shockwaves racing outward, sweeping up surrounding gas and dust, creating expanding shells of glowing material called supernova remnants. These remnants can shine for thousands of years, gradually fading as they spread across space. They glow in many wavelengths, from radio waves to X-rays, each revealing different aspects of the explosion. The Crab Nebula, for example, is the remnant of a supernova observed by astronomers in the year 1054. Nearly 1,000 years later, it still glows brightly, powered by a rapidly spinning pulsar at its center. Supernova remnants are more than just beautiful, they're crucial to the galaxy's evolution. The explosion disperses heavy elements like carbon, oxygen, and iron into space, enriching the interstellar medium and providing the raw materials for future stars and planets. These glowing clouds are the echoes of stellar death, fading slowly but never forgotten, drifting outward into the cosmic night. Far from the sun, comets are little more than dirty snowballs, frozen chunks of ice, rock, and organic material drifting silently through space. But as a comet's orbit brings it closer to the sun's warmth, something beautiful happens. The ice begins to sublimate, turning directly from solid to gas, releasing dust and vapor that stream away from the comet's nucleus. This creates two distinct tails, a bluish ion tail pushed straight back by the solar wind, and a curved dust tail swept back by the pressure of sunlight. These tails can stretch for millions of kilometers, glowing softly against the darkness. The tails always point away from the sun, no matter which direction the comet is traveling, shaped by the invisible forces of radiation and solar wind. As the comet moves back into the outer solar system, the tails fade and the comet returns to its frozen silence. It's a cycle of awakening and sleep, driven by the comet's dance around the sun, a fleeting display of cosmic beauty. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space as they spin. When one of these beams points toward Earth, we detect a pulse, like a lighthouse beam flashing across the ocean. What makes pulsars extraordinary is their regularity. The fastest pulsars can spin hundreds of times per second, and they do so with astonishing precision. Their rotation rates are so stable that astronomers use them as cosmic clocks, some keeping time more accurately than atomic clocks on Earth. This precision arises from the physics of neutron stars, objects so dense and stable that once they're spinning, almost nothing can slow them down quickly. Over millions of years, they do gradually lose energy, but on human timescales, they're incredibly constant. Scientists have even proposed using pulsars for navigation in deep space, a kind of celestial GPS. These spinning remnants of dead stars, scattered across the galaxy, tick away with quiet, unyielding rhythm. Marking time in the darkness, among neutron stars, there exists a rare and extraordinary type called a magnetar. These objects possess magnetic fields 1 trillion times stronger than Earth's, the most powerful magnetic fields known to exist anywhere in the universe. A magnetar's field is so intense that it warps the very atoms around it, and if you were to get within 1,000 kilometers of one, the magnetic forces would distort your body at the molecular level. Occasionally, magnetars release bursts of energy called starquakes, sudden cracks in their crusts that unleash enormous flares of X-rays and gamma rays. One such flare, detected in 2004 from a magnetar 50,000 light-years away, briefly saturated detectors across the solar system and affected Earth's upper atmosphere. Despite their power, magnetars are small, only about 20 kilometers across, and they're incredibly rare. They represent an extreme state of matter where magnetic forces dominate, creating some of the most violent and energetic phenomena in the cosmos. Silent, spinning and magnetically fierce, they are the universe's quiet storm generators. In science fiction, we often imagine exotic worlds with twin suns rising over alien horizons. In reality, such planets exist. These are called circumbinary planets, worlds that orbit not one star but two, as the stars themselves orbit each other. The discovery of these planets has shown that planetary systems can form even in the complex gravitational environments of binary star systems. One famous example is Kepler 16b, a gas giant orbiting two stars locked in a close dance. If you stood on such a planet, you might see two suns in the sky, casting double shadows and creating unique patterns of light and darkness. The gravitational dynamics are intricate, with the planet tracing a path that keeps it stable despite the competing pulls from both stars. These systems challenge our understanding of how planets form and survive, showing that nature is more flexible and creative than we might have imagined. Under twin stars, worlds spin quietly, bathed in the glow of two distant fires. Despite their name, cosmic rays are not beams of light, but high-energy particles, mostly protons, that travel through space at nearly the speed of light. They originate from some of the universe's most violent events: supernova explosions, active galactic nuclei, and possibly even more exotic sources we don't fully understand. When these particles strike Earth's atmosphere, they collide with air molecules, creating cascades of secondary particles that rain down toward the surface. Most cosmic rays are deflected by Earth's magnetic field, but some reach the ground, and a few even pass through you as you sleep. Scientists study cosmic rays to learn about the extreme processes that accelerate them and to probe fundamental physics. Though invisible and mostly harmless at ground level, cosmic rays connect us to the distant, energetic corners of the universe, silent messengers from stellar explosions and supermassive black holes, arriving after journeys that may have lasted millions of years. Deep within the Sun, nuclear fusion creates immense heat and pressure, generating waves that ripple through its interior. These are pressure waves, essentially sound waves, but they travel through plasma instead of air. The Sun rings with these vibrations, oscillating in complex patterns that scientists study through a field called helioseismology. If we could somehow hear these sounds, the Sun would produce a deep, rumbling tone far below the range of human hearing. By analyzing these solar vibrations, astronomers can peer inside the Sun, mapping its internal structure, rotation, and dynamics in ways that would otherwise be impossible. The Sun is not silent, it hums, though its song is one we experience only through instruments. This constant vibration is a reminder that the Sun is not a static ball of fire, but a dynamic, living system, pulsing with energy, always in motion, resonating with the nuclear fire at its heart. When astronomers first observed planetary nebulae through early telescopes, they appeared as round, disc-like objects, similar in shape to planets. This led to the misleading name, which persists today, even though we now know they have nothing to do with planets at all. Planetary nebulae are actually the glowing shells of gas ejected by dying stars similar in size to our Sun. As these stars exhaust their nuclear fuel, they shed their outer layers into space, creating expanding clouds of ionized gas. At the center of each nebula sits the hot core of the original star, now a white dwarf, whose intense ultraviolet radiation causes the surrounding gas to glow in vivid colors. The shapes of planetary nebulae can be astonishingly complex: spheres, rings, butterflies, hourglasses, each shaped by the star's rotation, magnetic fields, and sometimes the influence of a companion star. These nebulae are the final breath of stars like our Sun, beautiful and ephemeral, glowing softly for thousands of years before fading into the interstellar medium. The Sun is not always calm. Occasionally, it releases sudden bursts of energy called solar flares, explosions of magnetic energy on its surface that release radiation across the electromagnetic spectrum. The most powerful flares are accompanied by coronal mass ejections, enormous clouds of charged particles that can hurtle toward Earth at millions of kilometers per hour. When these particles interact with Earth's magnetic field, they can induce electrical currents in power lines, pipelines, and other infrastructure. In 1989, a powerful geomagnetic storm caused by a solar flare knocked out the power grid in Quebec, leaving millions without electricity for hours. If an even larger event like the Carrington event of 1859 were to occur today, it could cause widespread damage to satellites, communications networks, and power systems. Fortunately, scientists monitor the sun constantly, providing warnings when dangerous flares occur. These solar outbursts are reminders that we live within the sun's sphere of influence, connected to its rhythms and storms even across over 150 million kilometers of space. Stars like our sun don't burn forever. After billions of years of fusing hydrogen into helium, they begin to run out of fuel. When this happens, the core contracts and heats up, while the outer layers expand dramatically. The star becomes a red giant, swelling to hundreds of times its original size. For our sun, this transformation will occur in about 5 billion years, and when it does, it will likely engulf Mercury, Venus, and possibly even Earth. These planets will spiral inward, their orbits decaying as they drag through the sun's expanded outer atmosphere until they're consumed entirely. The sun will shine brilliantly as a red giant for a time before shedding its outer layers and collapsing into a white dwarf. This is the fate awaiting most sun-like stars, a slow, inevitable expansion followed by a quiet cooling. The inner worlds will be lost, but the outer planets may survive, orbiting a dim stellar remnant in a cold, darkened solar system. Most stars explode only once, in a final supernova that marks their death. But there's a rare and strange type of stellar explosion that can happen multiple times. These are called recurrent novae, and they occur in binary star systems where a white dwarf pulls material from a companion star. As gas accumulates on the white dwarf's surface, it heats up and compresses until it reaches the point of runaway fusion, causing a brilliant thermonuclear explosion. This explosion doesn't destroy the white dwarf, it simply blows off the accumulated material. Over time, the white dwarf continues pulling gas from its companion, and the cycle repeats. Some recurrent novae have been observed erupting every few decades. There's also a theoretical phenomenon called a pair instability supernova, which might cause a star to undergo multiple explosive pulses before finally tearing itself apart. These repeating explosions remind us that the universe is filled with cycles, even in death. Stars can flare, fade, and flare again, pulsing with light across decades or centuries. Our galaxy, the Milky Way, is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. The two are rushing toward each other at about 110 kilometers per second, drawn together by mutual gravity. In approximately 4 billion years, they will begin to merge, a slow, graceful collision that will reshape both galaxies over hundreds of millions of years. Despite the dramatic scale, individual stars are so far apart that actual collisions between them will be extremely rare. Instead, the galaxies will pass through each other, their shapes distorting and stretching under gravitational forces, eventually settling into a single, larger elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda. The night sky will change dramatically during the merger, with new star formation triggered by colliding gas clouds, and the sky filled with the light of a combined galactic core. It's a slow cosmic dance already underway, though it will take billions of years to complete. Not all stellar objects manage to ignite nuclear fusion in their cores. Brown dwarfs are objects too massive to be planets, but not quite massive enough to become true stars. They form the same way stars do from collapsing clouds of gas, and dust, but they don't accumulate enough mass to sustain the fusion of hydrogen into helium. Most brown dwarfs are between 13 and 80 times the mass of Jupiter, a range sometimes called the substellar realm. They do emit some light and heat, usually in the infrared, from the energy of their initial collapse and, in some cases, from limited fusion of deuterium, a heavier form of hydrogen. But they're dim, cool, and difficult to detect. Brown dwarfs drift through space in a kind of stellar limbo, too big to be planets, too small to be stars, glowing faintly in the darkness. They're relatively common, scattered throughout the galaxy, quiet remnants of star formation that never quite ignited. The carbon in your body, the oxygen you breathe, the calcium in your bones, all were forged in the cores of stars and scattered across space by supernova explosions. When a massive star reaches the end of its life, it undergoes a series of fusion reactions creating heavier and heavier elements up to iron, but iron fusion doesn't release energy, it consumes it, so the core collapses suddenly, triggering a supernova. In the intense heat and pressure of the explosion, elements heavier than iron like gold, silver, and uranium are synthesized in just seconds. These elements, along with all the lighter ones created during the star's life, are blasted into space, enriching the interstellar medium. Over time, this enriched material gathers into new clouds, which collapse to form new stars and planets. Earth and everything on it is made from the debris of ancient stars. We are, quite literally, stardust, assembled from the remains of stellar explosions that occurred billions of years ago. In the early universe, when galaxies were young and chaotic, some of them hosted incredibly bright cores called quasars. These are among the most luminous objects in the universe, capable of outshining entire galaxies. At the heart of each quasar lies a supermassive black hole, millions or even billions of times the mass of the Sun, surrounded by a swirling disk of gas and dust. As material spirals inward toward the black hole, it heats up to millions of degrees, emitting intense radiation across the electromagnetic spectrum. Jets of particles are often launched from the poles of the accretion disk, traveling at nearly the speed of light and extending for thousands of light years. Quasars were most common in the early universe, when galaxies were still forming and merging, providing ample fuel for their central black holes. Today they're rare, but their light, traveling for billions of years, allows us to study the distant past. Quasars are cosmic beacons, showing us the violent, energetic youth of the universe. Gravity is not always gentle. When an object, whether a star, planet, or comet, gets too close to a massive body like a black hole or a planet, the difference in gravitational pull between the near side and far side can become extreme. This difference is called a tidal force, and if it's strong enough, it can literally pull the object apart. This process is known as spaghettification because the object is stretched into a long, thin shape like a noodle. Astronomers have observed this happening to stars that wander too close to supermassive black holes at the centers of galaxies. The star is torn apart, and its material forms a glowing accretion disk around the black hole, creating a brief, bright flare. Even within our solar system, tidal forces play a role. Comet Shoemaker Levy 9 was ripped into pieces by Jupiter's gravity before colliding with the planet in 1994. Tidal forces are a reminder that gravity, while invisible, can be incredibly powerful and destructive when conditions are extreme. As astronomers discover planets around other stars, they're finding worlds unlike anything we have in our own solar system. Hot Jupiters, for example, are gas giants that orbit extremely close to their stars, completing an orbit in just a few days and enduring scorching temperatures. Super-Earths are rocky planets larger than Earth but smaller than Neptune, a size category we don't have in our system. Mini-Neptunes are worlds slightly smaller than Neptune, with thick atmospheres and possibly icy or rocky cores. Some planets are tidally locked, with one side always facing their star in eternal day and the other in perpetual night. Others orbit in extreme ellipses or around binary stars. There are planets that rain glass sideways, planets with lava oceans, and planets orbiting the remnants of dead stars. The diversity of exoplanets has shattered our assumptions about planetary systems, revealing a universe far stranger and more varied than we imagined. Each discovery expands the boundaries of what we thought was possible. Far beyond the orbits of the planets, at the very edge of the Sun's gravitational influence, lies a vast, hypothetical cloud of icy bodies called the Oort cloud. Though it has never been directly observed, its existence is inferred from the orbits of long-period comets, which seem to come from a distant, spherical shell surrounding the solar system. The Oort cloud may contain trillions of objects, ranging from small chunks of ice to bodies the size of mountains, all drifting in the cold darkness. It's thought to extend from about 2,000 astronomical units from the Sun, nearly a quarter of the way to the nearest star, out to perhaps 100,000 astronomical units or more. Occasionally, a passing star or gravitational perturbation from the galaxy nudges one of these icy objects inward, sending it on a long journey toward the inner solar system, where it becomes a comet. The Oort cloud is a relic of the solar system's formation, a frozen archive of primordial material, waiting quietly at the edge of the Sun's reach. Most stars orbit the center of the Milky Way at relatively stable speeds bound by gravity, but occasionally a star is flung outward at incredible velocity, fast enough to escape the galaxy entirely. These are called hypervelocity stars, and they travel at speeds of up to 1,000 kilometers per second or more. Most are thought to be ejected by interactions with the supermassive black hole at the galaxy's center. If a binary star system gets too close, the black hole can capture one star and fling the other away at tremendous speed. Other hypervelocity stars may be ejected by supernova explosions in binary systems or by gravitational slingshots from dense star clusters. These runaway stars are racing toward intergalactic space, leaving the Milky Way behind forever. They're rare, difficult to detect, and their journeys will take them into the vast emptiness between galaxies, solitary wanderers drifting through the cosmic void. Not all supernovae come from the collapse of massive stars. Some occur when a white dwarf, the dense remnant of a sun-like star, accumulates too much mass. This usually happens in a binary system where the white dwarf pulls gas from a companion star. As the white dwarf's mass approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, the pressure and temperature in its core reach critical levels, triggering runaway carbon fusion. The entire star is consumed in a thermonuclear explosion, a Type Ia supernova. These explosions are remarkably uniform in brightness, making them useful as standard candles for measuring cosmic distances. Observations of distant Type Ia supernovae in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy. These stellar detonations, though catastrophic, have been essential tools for understanding the structure and fate of the universe, shining with consistent brilliance across billions of light years. Not all planets orbit stars. Some drift alone, through the galaxy, unbound to any solar system, traveling through the darkness of interstellar space. These rogue planets may have been ejected from their original systems by gravitational interactions with other planets or passing stars, or they may have formed independently in the collapse of small gas clouds. They're difficult to detect because they emit almost no light, but astronomers have found evidence of them through microlensing events, where a rogue planet's gravity briefly magnifies the light of a background star. Some estimates suggest there could be billions of rogue planets in the Milky Way, perhaps even outnumbering stars. These wandering worlds are cold, dark and alone, drifting through space without a sun to warm them. If any have atmospheres or internal heat sources, they might even harbor subsurface oceans hidden beneath frozen crusts. They are the galaxy's orphans, sailing silently through the void. Some of the most active regions of star formation are hidden from view, cloaked in thick clouds of gas and dust that block visible light. These are called dark nebulae, and they appear as shadowy patches against the backdrop of stars. But within these opaque clouds, gravity is at work, pulling material together into dense clumps that will eventually ignite as new stars. Infrared telescopes can peer through the dust, revealing the hot young stars forming inside. One famous example is the Pillars of Creation in the Eagle Nebula, towering columns of gas and dust where stars are being born. These stellar nurseries are among the coldest places in the galaxy, with temperatures just a few degrees above absolute zero, yet they're the sites of intense activity. Over millions of years, the newborn stars will disperse the surrounding gas with their radiation and winds, eventually revealing themselves. But for now, they grow in darkness, hidden but full of potential. When a star explodes in a supernova, it releases a brief, brilliant flash of light that travels outward in all directions. Sometimes this light encounters clouds of gas or dust located far from the explosion. The light reflects off these clouds and travels toward Earth, arriving years, decades, or even centuries after the direct light from the supernova. This creates what's called a light echo, a delayed reflection that allows astronomers to study explosions that occurred long ago. Light echoes from supernovae observed hundreds of years ago have been detected and analyzed, providing insights into historical stellar explosions. In some cases, light echoes have revealed details about supernovae that were seen by ancient observers but not recorded with modern instruments. These echoes are like cosmic time capsules, carrying information about events that happened in the past, reflected off distant clouds and finally reaching us after a long journey through space. In recent years, astronomers have detected brief, intense bursts of radio waves coming from distant galaxies. These fast radio bursts, or FRBs, last only milliseconds, but in that short time they release as much energy as the Sun does in days. Most FRBs have been detected only once, appearing suddenly and never repeating, though a few have been seen to repeat at irregular intervals. The source of these bursts remains uncertain. Theories include magnetars, colliding neutron stars, or even more exotic possibilities like evaporating black holes or advanced civilizations. The bursts travel across billions of light years, carrying information about the material they pass through, which can help astronomers study the structure of the universe. Despite their mystery, FRBs are detected regularly now thanks to improved radio telescopes. They're one of the newest puzzles in astronomy, flashes of energy from the depths of space, brief and brilliant, arriving without warning. Magnetic fields aren't confined to planets and stars. They exist throughout the universe, threading through galaxies, nebulae, and the space between stars. These cosmic magnetic fields are typically weak, far weaker than a refrigerator magnet, but they span enormous distances and play crucial roles in shaping the cosmos. They guide the motion of charged particles, influence star formation, and help launch jets from black holes. In galaxies, magnetic fields follow spiral arms, aligned with the flow of gas and stars. In galaxy clusters, fields can stretch for millions of light years, affecting the hot gas that fills the space between galaxies. These fields are invisible to the eye, but astronomers can detect them by observing how they polarize light or affect the motion of particles. The universe is not just a web of gravity and light, but also of magnetism, a hidden force that threads through everything, guiding and shaping the cosmos in subtle, powerful ways. Not all galaxies shine brightly with stars. Some are so faint and diffuse that they're nearly invisible in regular telescopes. These ultra-diffuse galaxies can be as large as the Milky Way, but contain far fewer stars, spread so thinly that they barely register against the darkness of space. Some of these galaxies are made mostly of dark matter with only a sparse scattering of stars. Others may have had their gas stripped away by interactions with larger galaxies, halting star formation and leaving them dim and ghostly. Astronomers have only recently begun to discover and study these elusive objects, which challenge our understanding of how galaxies form and evolve. In some cases, they're detected not by their starlight, but by their gravitational effects or by faint glows in specific wavelengths. These invisible galaxies remind us that the universe is full of things we can't easily see, structures that exist in the shadows, waiting to be found. The universe is not evenly distributed. Galaxies tend to cluster together along filaments and sheets, forming a cosmic web. Between these structures lie enormous voids, regions of space with very few galaxies, stretching hundreds of millions of light-years across. These cosmic voids are the largest structures in the universe, vast expanses of near emptiness. Though they are not completely empty, they contain far less matter than average, mostly just sparse gas and the occasional lonely galaxy. The existence of these voids shapes the large-scale structure of the universe, affecting how galaxies move and cluster. Some voids are so large that light takes hundreds of millions of years to cross them. Within these quiet regions, space expands largely undisturbed, a gentle stretching of the fabric of the cosmos. Cosmic voids are the universe's breathing spaces, the pauses between the crowded clusters, where silence and darkness reign. Our sun occasionally releases powerful solar flares, but compared to some stars, it's relatively calm. Certain stars, especially young or magnetically active ones, can produce superflares, eruptions thousands of times more powerful than anything our sun has produced in recorded history. These superflares release tremendous amounts of radiation and charged particles, and if a planet orbits too close to such a star, the effects could be devastating. The intense radiation could strip away the planet's atmosphere, sterilize its surface, and make it uninhabitable for life as we know it. Some astronomers believe that superflares may have affected early Earth, potentially influencing the development of life or causing mass extinctions. For planets in the habitable zones of highly active stars, these eruptions pose a serious challenge to habitability. The flares can also trigger powerful auroras and geomagnetic storms on affected planets. While rare on sun-like stars, superflares remind us that the universe can be a harsh place, and the calm stability of our own sun is something of a cosmic gift. A gentle star that allows life to flourish undisturbed. Most binary stars orbit each other in simple ellipses, but in rare cases involving three stars of similar mass, something remarkable can happen. The stars can trace out a figure-8 pattern, weaving around each other in a complex, choreographed dance. This type of orbit is called a figure-8 or trefoil orbit, and it requires precise conditions, three stars of nearly equal mass arranged just right. The system is dynamically unstable over long periods, meaning it will eventually change or break apart, but while it lasts, it creates one of the most elegant patterns in orbital mechanics. These systems were first discovered through computer simulations before being confirmed in observations. The gravity of each star constantly pulls on the others, creating a delicate balance that allows them to trace their looping paths through space. It's a reminder that even gravity, which follows strict mathematical laws, can create patterns of unexpected beauty and complexity. When light from a distant galaxy passes near a massive object like a galaxy cluster, the intense gravity bends the light's path, much like a glass lens. This phenomenon, called gravitational lensing, can create multiple distorted images of the same background galaxy, sometimes stretched into arcs or even complete rings called Einstein rings. In some cases, the lensing magnifies the distant galaxy, allowing astronomers to study objects that would otherwise be too faint to see. Gravitational lensing has become a powerful tool for studying dark matter, since the amount of bending reveals the total mass of the lensing object, including invisible dark matter. It's like the universe providing us with natural telescopes, magnifying distant corners of space. These cosmic mirages are not illusions but real light, bent and multiplied by the curvature of space-time itself. Every warped arc is a reminder that mass shapes the very fabric of space, turning the cosmos into a hall of gravitational mirrors. At the centers of some galaxies, supermassive black holes devour material from accretion disks, and in the process, they can launch enormous jets of particles and radiation perpendicular to the disk. These jets travel at nearly the speed of light and can extend for millions of light years into intergalactic space, far beyond the galaxy itself. The jets are powered by magnetic fields and the rotational energy of the black hole, channeling material and energy outward in narrow, focused beams. When these jets collide with intergalactic gas, they can create vast lobes of radio emission visible to radio telescopes. Some jets appear to point directly at Earth, creating incredibly bright sources called blazars. These galactic jets are among the largest single structures in the universe, bridges of energy connecting galactic cores to the cosmic web beyond. They're powered by the smallest, densest objects we know, black holes, yet they reach across the vastest scales, influencing the evolution of galaxies and the space between them. When a star like our Sun dies, it sheds its outer layers and leaves behind a dense core called a white dwarf. Planets that survived the star's red giant phase can continue orbiting this stellar remnant, now just a fading ember. Astronomers have discovered planets orbiting white dwarfs, detected through their gravitational effects or by observing transits as they pass in front of the dim star. Even more remarkably, planets have been found orbiting pulsars, the rapidly spinning neutron stars left behind by supernova explosions. These pulsar planets likely formed from the debris of the explosion itself, making them second-generation worlds born from stellar death. The environments around these dead stars are harsh, bathed in radiation, and lacking the warmth of a living sun, but the planets persist, orbiting in the darkness. They're reminders that planetary systems can survive stellar death, silent witnesses to the end of their parent stars, circling through eternal twilight. According to some theories, the early universe may have formed defects in the fabric of spacetime during phase transitions, creating one-dimensional structures called cosmic strings. These would be incredibly thin, perhaps smaller than an atom in width, but immensely dense, with a single meter of cosmic string containing more mass than Earth. If they exist, cosmic strings would stretch across the universe, possibly for billions of light years, creating gravitational effects that could be detected through their influence on light or the cosmic microwave background. They might even produce gravitational waves as they vibrate or interact. So far, no cosmic strings have been conclusively detected, but they remain a fascinating theoretical possibility. If found, they would offer a window into the physics of the very early universe, remnants of cosmic phase transitions that occurred fractions of a second after the Big Bang. These invisible threads would be ancient scars in space-time itself, woven into the fabric of reality. When a planetary system is young and still forming, it's a chaotic place. Multiple protoplanets orbit in a disk of gas and dust, and gravitational interactions between them can be violent. During this turbulent period, some planets can be flung out of the system entirely, sent hurtling into interstellar space as rogue planets. Computer simulations suggest that most planetary systems may have ejected one or more planets during their formation. Jupiter, in our own solar system, may have caused such ejections early in its history as it migrated inward and disturbed the orbits of other bodies. The ejected planets become cosmic wanderers, drifting through the galaxy without a sun. This process of ejection is thought to be common, which is why astronomers believe rogue planets may outnumber stars. These outcasts carry the memory of their violent youth, forever separated from the systems where they were born, traveling alone through the darkness. In dense environments like the cores of globular clusters, where stars are packed closely together, direct collisions between stars can occur. When two stars collide, the result depends on their masses, speeds, and angles of impact. Sometimes they merge, forming a single, larger star called a blue straggler, which appears younger and hotter than it should be for the cluster's age. In other cases, the collision can strip away the outer layers of one or both stars, creating unusual remnants. Very rarely, such collisions might trigger supernova-like explosions or form exotic objects like massive X-ray binaries. These stellar pileups are rare in most parts of the galaxy, where stars are well separated, but in the crowded hearts of ancient clusters, they happen often enough to shape the cluster's evolution. Each collision is a cosmic accident, two stars whose paths crossed in the vastness of space, merging their fates into something new and strange. Planetary nebulae, the glowing shells ejected by dying stars, come in a stunning variety of shapes. While some are simple spheres, many are far more complex, forming intricate structures like hourglasses, butterflies, spirals, and even cat's eyes. These shapes are sculpted by a combination of factors: the star's rotation, magnetic fields, and the influence of companion stars in binary systems. As the dying star ejects material, these forces channel the gas into specific directions, creating lobes, jets, and equatorial rings. The Butterfly Nebula, for example, shows two spectacular lobes extending in opposite directions, shaped by high-speed winds from the central star. The Hourglass Nebula displays a narrow waist surrounded by expanding rings. Each nebula is unique, a cosmic sculpture formed by the physics of stellar death. These beautiful structures are fleeting, lasting only tens of thousands of years before dispersing into space, but while they exist, they're among the most visually stunning objects in the sky. Stars don't just shine, they blow. All stars emit stellar winds, streams of charged particles flowing outward from their surfaces into space. Our sun's solar wind is relatively gentle, but more massive stars can produce winds so powerful they shape the surrounding interstellar medium. These winds can carve out bubbles in nearby gas clouds, compress material to trigger new star formation, or sweep away the atmospheres of nearby planets. In some cases, stellar winds from multiple stars in a cluster can combine to create enormous superbubbles, cavities hundreds of light years across. When a massive star nears the end of its life, its wind intensifies, blowing off huge amounts of mass and creating shells and nebulae around it. These winds are invisible to the eye, but their effects are profound, redistributing matter and energy throughout the galaxy. Every star breathes, exhaling particles and energy into the space around it, a constant stellar exhalation that never stops. While supernovae create many heavy elements, the very heaviest elements, like gold, platinum, and uranium, are primarily formed in an even more violent event, the collision of two neutron stars. When these incredibly dense stellar remnants spiral into each other, they merge in a cataclysmic explosion called a kilonova. The extreme conditions during this merger, with temperatures and densities beyond anything in a supernova, allow rapid neutron capture processes to occur, building up the heaviest elements in the periodic table. The collision also produces gravitational waves and gamma-ray bursts, making these events detectable across the universe. In 2017, astronomers observed a neutron star merger for the first time using both gravitational wave detectors and telescopes across the electromagnetic spectrum, confirming that these collisions are indeed the primary source of heavy elements. The gold in jewelry, the platinum in electronics, all were born in these cosmic smash-ups, forged in the merger of stellar corpses billions of years ago. Galaxies come in a beautiful variety of forms. Spiral galaxies, like our Milky Way, have graceful curved arms winding outward from a central bulge, rich with young stars and glowing gas. Elliptical galaxies are smooth, featureless collections of stars, ranging from nearly spherical to elongated ovals, typically populated by older, redder stars with little active star formation. Irregular galaxies lack defined structure, appearing as chaotic, asymmetric clouds of stars and gas, often shaped by gravitational interactions or mergers. There are also lenticular galaxies, disc-shaped like spirals but without prominent arms. Each type tells a story about the galaxy's history and evolution. Spirals are often still forming stars with rotating disks of gas, fueling new generation. Ellipticals may have formed from the merger of smaller galaxies, their orderly rotation disrupted into random stellar orbits. Irregular galaxies are often young or disturbed, their shapes reflecting recent chaos. Together, these different forms paint a picture of the diverse ways matter can organize itself across the cosmos. The Sun occasionally releases huge bubbles of plasma called coronal mass ejections, sending billions of tons of charged particles hurtling through space at millions of kilometers per hour. When one of these eruptions reaches Earth, the particles interact with our planet's magnetic field, creating geomagnetic storms. These storms funnel particles down toward the poles, where they collide with atmospheric gases, causing them to glow in brilliant colors. The result is an aurora, shimmering curtains and arcs of green, red, purple, and white light dancing across the polar skies. During powerful storms, auroras can be seen much farther from the poles than usual, sometimes visible from mid-latitudes. The colors depend on which gases are being excited. Oxygen produces green and red, nitrogen creates purple and blue. Watching an aurora is witnessing the direct interaction between our planet and the Sun, a visible manifestation of the solar wind's energy painting the atmosphere with light. It's a peaceful display of cosmic forces, beautiful and quiet. Glowing in the darkness, in 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky, no larger than a grain of sand held at arm's length, and took a long exposure over several days. The result was astonishing. The Hubble Deep Field image revealed not emptiness, but thousands of galaxies, each containing billions of stars, stretching back billions of light years. This single image transformed our understanding of the universe's vastness and population. Later, even deeper images like the Hubble Ultra Deep Field and the Extreme Deep Field revealed galaxies from when the universe was less than 1 billion years old, showing us the cosmos in its youth. These images demonstrate that no matter where we look, the universe is filled with galaxies, each a vast island of stars separated by immense distances. The deep fields are humbling, showing us the incredible richness of the cosmos and reminding us that our own galaxy is just one of hundreds of billions, scattered across space and time. When two galaxies merge, their central supermassive black holes eventually sink to the center of the new, combined galaxy. There, they begin orbiting each other, slowly spiraling inward over millions or even billions of years. During this long dance, they emit gravitational waves which carry away energy and angular momentum, causing the orbit to decay. Eventually, when they're close enough, the black holes merge in a final, violent collision that releases a tremendous burst of gravitational waves. But before that moment, they can orbit each other for an immensely long time, locked in a gravitational embrace. Astronomers have identified several binary supermassive black hole systems detected through the motion of stars around them or through periodic variations in their light. These systems offer a window into the final stages of galaxy mergers and the growth of the largest black holes in the universe. Two invisible giants circling each other in the darkness, waiting for their inevitable union. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this brief moment, space itself expanded faster than the speed of light, growing from smaller than an atom to potentially larger than the observable universe today. This doesn't violate relativity because it's space itself expanding, not objects moving through space. Inflation solves several puzzles about the universe, including why it appears so uniform in all directions, and why it's geometrically flat. The theory also predicts the existence of tiny quantum fluctuations that were stretched to cosmic scales during inflation, becoming the seeds of all galaxies and large-scale structures. While inflation happened almost 14 billion years ago and lasted less than a second, its effects are still visible today in the distribution of galaxies and the patterns in the cosmic microwave background. It was a moment of incredible growth, setting the stage for everything that followed. Among the most massive and luminous stars in the universe are Wolf-Rayet stars, evolved giants that have shed their outer hydrogen layers to reveal extremely hot, bare cores. These stars blow powerful stellar winds at speeds of thousands of kilometers per second, losing mass at an incredible rate. A single Wolf-Rayet star can lose the equivalent of Earth's mass every few thousand years, ejecting material into space with such force that it creates glowing nebulae around the star. These winds are driven by intense radiation pressure from the star's blazing surface, which can reach temperatures of 100,000 degrees or more. Wolf-Rayet stars are rare and short-lived, existing for only a few 100,000 years before exploding as supernovae. Their fierce winds enrich the surrounding space with heavy elements and can trigger star formation in nearby clouds. Their stellar furnaces burning fiercely and fast, their winds sculpting the interstellar medium around them. Some of the most intricate structures in planetary ring systems are maintained by small moons called shepherd moons. These tiny satellites orbit just inside or outside narrow rings, and their gravity keeps the ring particles confined to a specific path. As particles drift too far inward or outward, the shepherd moon's gravity nudges them back into place. Saturn's F-ring is a prime example, with two shepherd moons, Prometheus and Pandora, creating a narrow, braided ring structure. These moons also create waves and gaps in the rings as they orbit, sculpting the ring material into intricate patterns. Some shepherd moons are only a few kilometers across, but their gravitational influence is crucial for maintaining the sharp edges and fine structures we observe in ring systems. They're cosmic shepherds, quietly tending their flocks of ice and rock, keeping order in the delicate ring structures that encircle giant planets. Cepheid variables are stars that brighten and dim in a regular, predictable cycle, pulsing like cosmic heartbeats. This pulsation is caused by the star's outer layers expanding and contracting due to changes in opacity and temperature. What makes Cepheids especially valuable is the relationship between their pulsation period and their intrinsic brightness. The longer the period, the brighter the star. This means astronomers can measure a Cepheid's period, determine its true brightness, and then calculate its distance by comparing that to how bright it appears from Earth. Cepheids have become one of the most important tools for measuring cosmic distances, allowing astronomers to map the scale of our galaxy and beyond. They're stellar measuring sticks pulsing with rhythms that reveal the vastness of space. Henrietta Swan Leavitt discovered this relationship in the early 1900s, and it revolutionized our understanding of the universe's size. These variable stars continue to pulse today, reliable cosmic beacons marking distances across the cosmos. Small dwarf galaxies often orbit larger galaxies like the Milky Way, bound by gravity in a slow orbital dance. Over time, the gravitational pull of the larger galaxy can strip stars and gas from the dwarf galaxy, gradually dismantling it. Some dwarf galaxies are completely absorbed, their stars scattered throughout the larger galaxy's halo. Others leave behind stellar streams, long ribbons of stars that trace their former orbits. The Milky Way is currently in the process of consuming several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which is being pulled apart and absorbed. This process of galactic cannibalism is thought to be common and plays an important role in how large galaxies grow over time. The dwarf galaxies don't vanish completely, their stars become part of the larger galaxy, but they lose their identity as separate systems. It's a slow, inevitable process driven by gravity's patient pull, reshaping the cosmic landscape star by star. When stars are born from collapsing clouds of gas and dust, they often launch narrow jets of material from their poles. These stellar jets are powered by the rotation of the accretion disk surrounding the young star and guided by magnetic fields. The jets can extend for light years, traveling at hundreds of kilometers per second and creating glowing shock waves where they collide with surrounding gas. These jets help remove excess angular momentum from the forming star system, allowing material to continue falling onto the growing star. In some cases, jets from young stars create beautiful nebulae called Herbig-Haro objects, glowing clouds shaped by the impact of the jets. Observing these jets gives astronomers insight into the star formation process and the early evolution of planetary systems. Even our own sun may have had jets when it was young, though they've long since faded. These outflows are the birth cries of stars, energetic blasts that announce the arrival of new light in the galaxy. Surrounding every galaxy is an extended halo of dark matter, an invisible substance that doesn't emit, absorb, or reflect light. This dark matter halo is far larger than the visible galaxy, extending well beyond the disk of stars and gas. We know these halos exist because of their gravitational effects. Stars in the outer parts of galaxies orbit faster than they should based on the visible mass alone, suggesting the presence of additional unseen matter. Dark matter makes up about 85% of the matter in the universe, yet we still don't know what it is. It could be composed of exotic particles that interact only through gravity, or something even stranger. The dark matter halos around galaxies help hold them together and play a crucial role in galaxy formation and evolution. They're invisible scaffolds providing the gravitational framework within which galaxies take shape and grow. We live in a galaxy wrapped in dark matter, a vast, unseen presence that shapes our cosmic home. In some binary star systems, one star has evolved into a compact object, a white dwarf, neutron star, or black hole, while the other remains a normal star. The compact object's strong gravity pulls material from its companion, forming an accretion disk around itself. As this stolen matter spirals inward, it heats up to millions of degrees and emits powerful X-rays. These systems are called X-ray binaries, and they're some of the brightest X-ray sources in the sky. The process is a kind of stellar vampirism, with the compact object feeding on its companion, slowly draining it of mass. In some cases, this transfer can trigger violent outbursts or explosions. X-ray binaries provide laboratories for studying matter under extreme conditions, including the effects of strong gravity and intense magnetic fields. They're cosmic parasites, shining brightly in X-rays as they consume their companions, locked in an intimate but destructive relationship. Around young stars, flat rotating disks of gas and dust often form, called protoplanetary disks. Within these disks, particles collide and stick together, gradually growing from dust grains to pebbles to boulders and eventually to planets. This process takes millions of years, and the disk provides all the raw materials needed to build a planetary system. Observations of protoplanetary disks have revealed gaps and rings, likely created by forming planets clearing out their orbital paths. Some disks show spiral structures, possibly driven by gravitational instabilities or the influence of unseen planets. These disks are planetary nurseries where worlds are assembled grain by grain. Our own solar system formed from such a disk about 4.6 billion years ago, and today we can observe similar disks around other stars, watching the planet formation process in action. Each disk is unique, shaped by the mass of the star, the composition of the material, and chance events that determine which planets will form and where. Occasionally, a star wanders too close to the supermassive black hole at a galaxy's center. When this happens, the black hole's gravity tears the star apart in a process called a tidal disruption event. About half of the star's material is flung out into space while the rest falls into an accretion disk around the black hole. As this material spirals inward, it heats up and produces a brilliant flare of light that can outshine the entire galaxy for weeks or months. Astronomers have observed dozens of these events, each providing a unique opportunity to study black holes and the physics of extreme gravity. The flares occur across various wavelengths, from optical light to X-rays and ultraviolet. They're rare, unpredictable events, cosmic tragedies, where individual stars meet their end, torn apart and consumed by the darkness at the galaxy's heart. Each flare is a star's final light, a bright farewell before disappearing into the black hole's grasp. When galaxies collide, they don't actually crash into each other like solid objects. Instead, they pass through one another, with individual stars rarely touching due to the vast distances between them. However, the gravitational interaction is dramatic. Gas clouds within the galaxies are compressed and shocked, triggering intense bursts of star formation. These starburst galaxies can form stars hundreds of times faster than the Milky Way, creating brilliant regions of young, hot stars and glowing nebulae. The collision also distorts the galaxy's shapes, pulling out long tidal tails and bridges of stars and gas. Over hundreds of millions of years, the two galaxies merge into one, their stars, gas, and dark matter mingling and settling into a new configuration. The resulting galaxy is often an elliptical, having lost the spiral structure of its progenitors. These cosmic collisions are beautiful and creative processes, destroying old structures but birthing vast numbers of new stars in spectacular displays of galactic renewal. Not all black holes lurk alone in the darkness. Some exist in binary systems with ordinary stars, locked in mutual orbit. In these systems, the black hole's gravity can pull material from its companion, forming an accretion disk. As matter spirals inward, it emits X-rays, making the system visible to X-ray telescopes, even though the black hole itself is invisible. Some stellar mass black holes have been detected this way, through their gravitational effects on visible companions and the X-rays produced by accretion. In rare cases, the black hole and its companion are so close that the orbital period is just hours. These systems are the remnants of binary stars where one member exploded as a supernova and left behind a black hole. The surviving star continues its orbit, now circling an invisible partner. These binaries are cosmic odd couples, darkness and light bound together, dancing through space in a relationship shaped by gravity and stellar evolution. For decades, scientists wondered where cosmic rays, those high-energy particles that bombard Earth from space, actually come from. Evidence now suggests that many are accelerated in the expanding shock waves of supernova remnants. As the blast wave from a supernova plows through surrounding gas, it creates turbulent magnetic fields that can trap and accelerate charged particles to incredible energies. Some of these particles escape the remnant and travel through the galaxy, eventually reaching Earth. Observatories have detected gamma rays from supernova remnants, confirming that particle acceleration is occurring there. However, the highest energy cosmic rays, which carry far more energy than supernova remnants can explain, may come from even more exotic sources like active galactic nuclei or gamma ray bursts. These energetic particles connect us to distant violent events, messengers from supernova explosions that occurred thousands or millions of years ago, now arriving to streak through our atmosphere and occasionally through us. When astronomers first began discovering planets around other stars, they found something unexpected: gas giant planets orbiting much closer to their stars than any planet in our solar system. These so-called hot Jupiters orbit within a few million kilometers of their stars, completing an orbit in just days or even hours. At such close distances, they're heated to scorching temperatures, often over 1,000 degrees Celsius, with their atmospheres puffed up by the intense stellar radiation. Some hot Jupiters are tidally locked, with one side perpetually facing the star, in eternal day and the other in permanent night. This creates extreme temperature differences and powerful winds that race around the planet. Hot Jupiters likely didn't form so close to their stars. Instead, they probably formed farther out and then migrated inward due to gravitational interactions with other planets or the protoplanetary disk. These worlds challenged our theories of planetary formation and showed that our solar system's architecture is just one of many possible configurations. Most galaxies, like the Milky Way, form a few stars per year. But some galaxies, called starburst galaxies, can create hundreds or even thousands of stars annually. These intense periods of star formation are often triggered by galaxy collisions or mergers, which compress gas clouds and ignite vast stellar nurseries. Starburst galaxies shine brightly in infrared and ultraviolet light, glowing with the heat and radiation from millions of young, massive stars. The starburst phase is relatively brief in cosmic terms, typically lasting only a few 100 million years before the galaxy exhausts its gas supply or the stellar winds and supernovae from the new stars blow away the remaining fuel. During this time, the galaxy transforms dramatically, converting much of its gas into stars. These galaxies are like cosmic fireworks, brilliant and ephemeral, burning through their resources in a spectacular display of stellar creation. Our galaxy, along with thousands of others in our local region of the universe, is drifting toward a mysterious area of space called the Great Attractor. This region, located about 150 million light-years away, contains an enormous concentration of mass that exerts a gravitational pull on surrounding galaxies. The Great Attractor itself is partially hidden behind the plane of the Milky Way, making it difficult to observe directly. Observations suggest it's not a single structure, but rather a complex of galaxy clusters and superclusters. Our motion toward it is part of a larger flow pattern in the universe, where galaxies stream along invisible currents defined by the distribution of dark matter and visible mass. We're moving toward the Great Attractor at about 600 kilometers per second, a journey that will take hundreds of millions of years. It's a reminder that even galaxies are not stationary, but drift through space, pulled by unseen masses in a cosmic choreography. Though they're among the most beautiful objects in the night sky, planetary nebulae are fleeting. These glowing shells of gas, ejected by dying stars, expand outward at tens of kilometers per second. As they spread, they thin out and gradually fade. Most planetary nebulae last only 10,000 to 50,000 years before they become too diffuse to see. This is incredibly brief compared to stellar lifetimes, which span billions of years. The central star, now a white dwarf, continues to shine for much longer, but the surrounding nebula disperses into the interstellar medium, mixing with the gas and dust between stars. This recycled material will eventually be incorporated into new generations of stars and planets. The ephemeral nature of planetary nebulae makes them precious, cosmic flowers that bloom for just a moment in astronomical time, brilliant and beautiful, before fading back into the darkness from which they came. Around many young stars, astronomers have observed protoplanetary disks with distinct gaps and rings like the grooves in a vinyl record. These gaps are likely created by forming planets that have cleared out material along their orbital paths. As a planet grows, its gravity pulls in nearby dust and gas, creating a gap that becomes more pronounced over time. Multiple gaps suggest multiple planets are forming at different distances from the star. The ALMA radio telescope has captured stunning images of these structures, revealing the planet formation process in unprecedented detail. Some disks show spiral arms, possibly created by planets perturbing the disk material. These observations confirm theories about how planets form and allow astronomers to detect planets before they're massive enough to see directly. Each gap is a signpost marking the location of a world being born, slowly gathering material and carving out its place in a nascent solar system. The largest stars in the universe are called hypergiants or supergiants, and they're almost incomprehensibly enormous. Stars like UY Scuti or Stephenson 2E18 have radii hundreds of times larger than the Sun. If you placed one of these stars at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, and Mars. Despite their enormous size, these stars are not particularly massive in terms of total mass, often only tens of times the Sun's mass. They've swollen to such proportions because they're in the late stages of stellar evolution, having exhausted their core hydrogen and expanded tremendously. Their outer layers are tenuous, with densities lower than Earth's atmosphere at sea level. These giants are rare and short-lived, destined to end their lives in spectacular supernova explosions. For now, they shine as beacons across the galaxy, vast and luminous, dominating their stellar neighborhoods. Just as planets orbit stars, moons orbit planets. While we haven't yet definitively detected moons around exoplanets, astronomers believe they must exist. The challenge is that exomoons are much smaller and dimmer than planets, making them incredibly difficult to detect. However, several candidate exomoons have been proposed based on subtle variations in planetary transit data or gravitational interactions. If confirmed, these would be the first moons discovered beyond our solar system. Some exomoons could be quite large, potentially Earth-sized or larger, especially if they orbit gas giants. In certain configurations, an exomoon orbiting in a star's habitable zone could potentially support life, even if its host planet is a gas giant. The search for exomoons is ongoing, using increasingly sophisticated techniques to detect these small worlds. Finding them would add another layer to the diversity of planetary systems and might reveal new places where life could exist. Neutron stars have incredibly strong crusts made of atomic nuclei crushed together under immense pressure. Despite this strength, the crust can crack and shift, particularly in magnetars, neutron stars with exceptionally powerful magnetic fields. These shifts, called starquakes, are similar to earthquakes but far more violent. A starquake can release as much energy in a fraction of a second as the Sun emits in years. The sudden movement rearranges the star's magnetic field and can trigger enormous bursts of X-rays and gamma rays that sweep across space. Some gamma-ray bursts may be caused by these starquakes rather than supernova explosions. The quakes happen because the neutron star's interior and crust rotate at different speeds, creating stress that eventually becomes too great for the crust to withstand. When it snaps, the release is explosive, a cosmic tremor in a star the size of a city, shaking the fabric of space-time itself. The Andromeda Galaxy, our nearest large galactic neighbor, is slightly larger than the Milky Way and contains an estimated 1 trillion stars. That's more than twice the number in our own galaxy. Andromeda is visible to the naked eye on dark nights as a fuzzy patch in the constellation Andromeda, and it's the most distant object you can see without a telescope, lying about 2.5 million light-years away. The galaxy has a similar spiral structure to the Milky Way, with a bright central bulge surrounded by graceful arms filled with young stars and glowing gas clouds. It also has a complex system of satellite galaxies orbiting around it. In about 4 billion years, Andromeda and the Milky Way will collide and merge, combining their trillion-plus stars into a single, larger galaxy. For now, Andromeda drifts through space toward us, a vast island of stars approaching slowly but inevitably across the cosmic void. On the largest scales, the universe is not uniformly distributed but organized into a vast cosmic web. This web consists of enormous filaments of dark matter and gas that stretch across hundreds of millions of light-years, connecting galaxy clusters like threads in a tapestry. Between these filaments lie great voids, regions with very few galaxies. The filaments contain most of the universe's ordinary matter, though much of it is in the form of hot, diffuse gas that's difficult to detect. Galaxies tend to form and cluster along these filaments, drawn together by gravity. The structure resembles a three-dimensional spider web or the neural networks in a brain, with dense nodes connected by long, thin threads. Mapping this cosmic web helps astronomers understand how matter is distributed across the universe and how structures evolved over billions of years. The filaments are shaped by dark matter's gravity, which acts as an invisible framework guiding the flow of visible matter. This web is the largest known structure in the universe, a pattern that emerges only when you look at scales of billions of light years, revealing the universe's grand architecture. Pulsars are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams sweeping across the ocean. If one of these beams happens to point toward Earth during the star's rotation, we detect a pulse of radio waves. The pulses are incredibly regular, arriving with such precision that they were initially mistaken for signals from an alien civilization when first discovered in 1967. Different pulsars have different spin rates, from once every few seconds to hundreds of times per second. The fastest spinning pulsars, called millisecond pulsars, rotate so quickly that their surfaces are moving at a significant fraction of the speed of light. These cosmic lighthouses help astronomers study extreme physics, test general relativity, and even search for gravitational waves. They're the universe's natural timekeepers, ticking away with unwavering rhythm across the galaxy. In spiral galaxies like the Milky Way, gas doesn't simply sit still. It participates in a continuous cycle called the galactic fountain. Hot gas in the galactic disk, heated by supernova explosions and stellar winds, rises upward into the galaxy's halo, sometimes reaching heights of thousands of light-years above the disk. There, it cools and eventually falls back down toward the disk, where it can be incorporated into new stars. This cycle takes millions of years and plays a crucial role in regulating star formation and distributing heavy elements throughout the galaxy. The fountain also helps explain why galaxies don't exhaust their gas supply as quickly as they might otherwise. Some of the rising gas may escape the galaxy entirely, while fresh gas from the intergalactic medium falls in to replace it. The galaxy breathes, drawing in and expelling gas in a slow, steady rhythm that sustains its star-forming activity over billions of years. Brown dwarfs, often called failed stars, never achieved the mass needed to sustain hydrogen fusion in their cores, yet they're not completely dark. During their formation, gravitational collapse generated significant heat, and this residual warmth causes them to glow, primarily in infrared wavelengths. Young brown dwarfs can be relatively bright in infrared, but they cool steadily over time, gradually fading over billions of years. Some brown dwarfs are warm enough to have weather systems with clouds made of molten iron or silicate minerals. Others are so cool they have water clouds with temperatures similar to a pleasant day on Earth. These objects blur the line between planets and stars, sharing characteristics with both. They drift through the galaxy in quiet solitude, too small to shine like stars but too massive to be planets, glowing faintly in the darkness with the memory of their formation. The most active regions of star formation in the galaxy are often invisible in optical light, hidden behind thick veils of cosmic dust. These dust clouds absorb visible light from the forming stars within, making the nurseries appear as dark patches against the background of stars. However, the dust is warmed by the hidden stars and re-radiates that energy as infrared light, which can pass through the dust relatively easily. Infrared telescopes like Spitzer and the James Webb Space Telescope can peer through these dusty shrouds, revealing the star formation happening inside. What appears dark to our eyes is actually a bustling stellar maternity ward, filled with protostars, accretion disks, and planetary systems in the making. The dust itself is part of the birth process, providing the raw material that will eventually form planets. These hidden nurseries remind us that the universe has many secrets, and not everything that's important can be seen in visible light. When galaxies merge, their central supermassive black holes don't always settle peacefully into the center of the new combined galaxy. Sometimes a black hole can receive a gravitational kick during the merger, sending it careening through the galaxy or even ejecting it into intergalactic space. These rogue black holes would be invisible unless they happen to accrete nearby gas or disrupt the orbits of stars they pass near. Computer simulations suggest that rogue, supermassive black holes may be more common than previously thought, wandering through galaxies or drifting through the emptiness between them. Stellar mass black holes can also become rogues, ejected from binary systems or given a kick during the supernova that created them. These wandering black holes are difficult to detect, silent and invisible travelers moving through space, their presence betrayed only by their gravitational effects on anything unfortunate enough to cross their path. If you look at the western sky just after sunset or the eastern sky before sunrise from a very dark location, you might see a faint, triangular glow extending up from the horizon along the ecliptic. This is zodiacal light, and it's caused by sunlight reflecting off countless tiny dust particles scattered throughout the inner solar system. These particles are remnants from comets, collisions between asteroids, and leftover debris from the solar system's formation. They're spread in a disk roughly aligned with the planet's orbital plane. As sunlight hits these dust grains, they scatter the light toward Earth, creating the subtle glow. Zodiacal light is best seen from the tropics or during certain times of year, when the ecliptic makes a steep angle with the horizon. It's a reminder that space isn't perfectly empty. Even in our own solar system, there's a thin haze of dust, a cosmic fog that catches the sun's light and glows softly in the twilight sky. Orbiting in the halos of galaxies are dense, spherical collections of stars called globular clusters. These clusters can contain hundreds of thousands or even millions of stars packed into a region just tens of light years across, making them some of the most crowded stellar environments in the universe. The stars in globular clusters are among the oldest in the galaxy, often over 12 billion years old, dating back to the early history of galaxy formation. They're composed mostly of hydrogen and helium with very few heavier elements, reflecting the primordial composition of the early universe. In the core of a globular cluster, stars are so close together that they can interact gravitationally, sometimes forming exotic systems like blue stragglers or binary pulsars. These clusters are stellar fossils, ancient cities of stars that have remained largely unchanged for billions of years, offering windows into the distant past and the early epochs of cosmic history. At the centers of some galaxies, supermassive black holes actively accrete vast amounts of matter, creating some of the most luminous objects in the universe, active galactic nuclei, or AGN. The accretion disk around the black hole can reach temperatures of millions of degrees, blazing brilliantly across all wavelengths from radio waves to gamma rays. In some cases, the AGN is so bright that it outshines the billions of stars in the rest of the galaxy combined. These objects were more common in the early universe when galaxies were still forming and merging, providing abundant fuel for their central black holes. Today, many galaxies, including our Milky Way, have supermassive black holes that are relatively quiet, with little material falling in. But when conditions are right and a black hole has access to fresh gas, perhaps from a collision with another galaxy, it can flare into activity, becoming an AGN and dominating the galaxy's light output for millions of years. Sometimes, a distant object in the solar system passes directly in front of a background star, briefly blocking its light. This event, called an occultation, provides a unique opportunity to study the object. By carefully timing when the star's light dims and returns, astronomers can determine the object's size, shape, and whether it has an atmosphere or even rings. This technique has been used to discover rings around asteroids and to study the atmospheres of distant dwarf planets like Pluto before spacecraft visited them. Occultations require precise predictions and coordination, as observers must be positioned along the narrow path where the shadow falls on Earth. The brief dimming, sometimes lasting only seconds, contains valuable information encoded in how quickly and how much the light fades. These stellar alignments are cosmic coincidences that provide natural experiments, allowing astronomers to probe objects billions of kilometers away using just the shadow they cast. When young stars launch jets of material from their poles, these jets sometimes collide with surrounding gas clouds at high speeds, creating glowing shock waves called Herbig-Haro objects. These are among the most beautiful and dynamic phenomena in star-forming regions, appearing as bright knots and filaments that change visibly over just a few years. The jets themselves travel at hundreds of kilometers per second, and when they slam into dense gas, they heat it to thousands of degrees, causing it to glow in specific wavelengths. Herbig-Haro objects are transient, lasting only tens of thousands of years as the young star's jets evolve and eventually shut off. They come in many shapes: bow shocks, multiple knots along a jet, or diffuse glowing regions. Observing these objects helps astronomers understand how young stars shed angular momentum and clear out the gas around them, processes essential to star and planet formation. They're the visible signs of stellar birth, markers of new stars announcing their arrival. When two galaxies pass close to each other or collide, their mutual gravitational pull doesn't just affect their cores. It also draws out long streams of stars and gas called tidal tails. These can stretch for hundreds of thousands of light years, extending far beyond the original boundaries of either galaxy. Tidal tails form because the gravitational pull is stronger on the near side of each galaxy than on the far side, stretching them in opposite directions. The antennae galaxies, for example, display two prominent tidal tails curving away from the collision zone. Eventually, some of the material in these tails may fall back into the merging galaxies, while some may escape entirely, becoming part of the intergalactic medium or even forming small dwarf galaxies. These graceful arcs and bridges of stars are the fingerprints of galactic encounters, visible evidence of the gravitational dance between massive collections of stars spread across cosmic distances. Most of the universe appears calm when viewed in visible light, but when astronomers observe the sky in gamma rays, the highest energy form of light, they see a much more violent cosmos. Gamma rays are produced by the most energetic events and objects: supernova explosions, colliding neutron stars, matter falling into black holes, and gamma ray bursts. Earth's atmosphere absorbs gamma rays, so these observations must be made from space by satellites like Fermi and Swift. These telescopes have revealed that the gamma ray sky is constantly changing, with sources flaring and fading, new bursts appearing without warning, and pulsars flashing with precise timing. Gamma ray astronomy opens a window onto extreme physics, showing us the universe's most powerful particle accelerators and most violent explosions. It's a reminder that beneath the apparent serenity of the night sky, the cosmos is alive with high-energy phenomena, processes so energetic they produce light that can be detected across billions of light years. The jets launched by forming stars don't just create nearby Herbig-Haro objects. In some cases, they extend for several light years into space, punching through the surrounding molecular cloud. These jets are remarkably collimated, staying narrow even over vast distances, guided by magnetic fields that keep the flow focused. As the jets travel, they interact with the ambient gas, creating a series of shock waves and glowing knots along their length. Some jets show evidence of periodic variations, with regularly spaced blobs suggesting that the young star's accretion rate fluctuates over time. The jets can also trigger star formation in the clouds they impact, compressing gas to the point where it begins to collapse. These stellar fountains are part of the feedback process that regulates star formation, removing material from the protostellar disk while also affecting the surrounding environment. They're powerful outflows from some of the universe's youngest stars, reaching across light years with surprising precision. Some active galactic nuclei have powerful jets that shoot out from the region near their supermassive black holes at nearly the speed of light. When one of these jets happens to point directly toward Earth, we see an extremely bright source called a blazar. Because we're looking straight down the jet, the emission appears much brighter than it would if we viewed it from the side, an effect called relativistic beaming. Blazars are among the most variable objects in the sky, brightening and fading dramatically over days or even hours as conditions in the jet change. They emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Studying blazars helps astronomers understand the physics of relativistic jets and the environments around supermassive black holes. These cosmic searchlights, accidentally pointing our way, offer a direct view into some of the most powerful phenomena in the universe, engines capable of accelerating particles to energies far beyond anything we can achieve on Earth. When massive stars, those with cores more than about 8 solar masses, exhaust their nuclear fuel, they can no longer support themselves against gravity. The core collapses in a fraction of a second, and the resulting rebound sends a shock wave through the star's outer layers, blasting them into space in a Type II supernova. What remains after this explosion depends on the core's mass. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that protons and electrons are crushed together to form neutrons. The entire mass of a star is compressed into a sphere only about 20 kilometers across. Neutron stars are some of the densest objects in the universe, second only to black holes. Some spin rapidly as pulsars, others have incredibly strong magnetic fields as magnetars, and some exist in binary systems where they accrete matter and produce X-rays. These stellar remnants are the compressed hearts of dead stars, exotic laboratories where matter exists in states impossible to recreate anywhere else. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. For our Sun, this zone currently extends from roughly the orbit of Venus to just beyond Mars. But this zone isn't static. As a star ages and evolves, its luminosity changes and the habitable zone shifts. When our Sun was young, it was dimmer, and the habitable zone was closer in. In the future, as the Sun brightens and eventually swells into a red giant, the habitable zone will move outward, eventually extending to where Jupiter and Saturn orbit today. This means that moons like Europa or Enceladus, currently frozen, might one day have liquid water on their surfaces. The shifting habitable zone affects the long-term prospects for life, as planets that are comfortable today may become too hot or too cold in the future. It's a reminder that stellar evolution shapes not just stars themselves, but the potential for life around them. Sometimes, a distant star passes almost exactly in front of an even more distant background star. When this happens, the foreground star's gravity acts as a lens, magnifying the background star's light. If the foreground star has a planet, the planet's gravity creates an additional brief spike in the magnification curve. This technique, called gravitational microlensing, has discovered dozens of exoplanets, including some of the most distant ever found and some in orbits that would be difficult to detect by other methods. Microlensing events are unpredictable and unrepeatable, each one a cosmic coincidence that lasts days to weeks. The technique is most sensitive to planets at intermediate distances from their stars, complementing other detection methods. Some microlensing discoveries include planets orbiting in the galactic bulge, thousands of light years away, and even rogue planets drifting through space without stars. Each event offers a unique snapshot, using gravity itself as a natural telescope to reveal worlds we could never see directly. Planets don't necessarily stay where they form. In the early days of a planetary system, when gas and dust still fill the protoplanetary disk, planets can migrate inward or outward due to gravitational interactions with the disk or with other planets. Jupiter, for example, may have migrated inward and then back outward in our solar system's early history, a journey that would have reshaped the orbits of other planets and scattered smaller bodies. This migration can explain why we see hot Jupiters orbiting close to their stars, giant planets that likely formed farther out and then spiraled inward. Migration can also lead to mean motion resonances, where planets orbit with periods in simple ratios, like 2-1 or 3-2. Some planetary systems may have been far more chaotic in their youth, with planets crossing orbits and ejecting one another before settling into stable configurations. The current arrangement of planets around any star is the result of billions of years of gravitational choreography, migrations, interactions, and gradual settling. In regions where many massive stars form close together, their combined stellar winds and supernova explosions can carve out enormous cavities in the interstellar medium called superbubbles. These bubbles can span hundreds of light years and are filled with hot, low-density gas heated to millions of degrees. The expanding shell of a superbubble compresses surrounding gas, sometimes triggering new waves of star formation at its edges. Over time, superbubbles can break through the disk of a galaxy, creating chimneys that allow hot gas to escape into the galactic halo or even into intergalactic space. Our Sun is currently inside a superbubble called the local bubble, created by supernovae that exploded millions of years ago. The bubble's low density affects the local environment, including the distribution of interstellar gas and cosmic rays near Earth. Superbubbles are one way that stars reshape their galactic neighborhoods, feeding back energy into the interstellar medium and influencing the next generation of star formation. The universe is expanding, and this expansion affects how we can travel through it. While light from distant galaxies can reach us, traveling across billions of light years, the space between us and those galaxies is expanding. For galaxies beyond a certain distance, space expands faster than light can travel through it. This means that no matter how fast a spacecraft traveled, even at the speed of light, it could never reach those distant galaxies. They are beyond what's called the cosmic event horizon. As the universe continues to expand and that expansion accelerates, more and more galaxies will cross this horizon and become forever unreachable. In the far future, distant galaxies will not just be unreachable but invisible, their light stretched to wavelengths so long and faint that they can no longer be detected. The observable universe will shrink, even as the actual universe continues to grow. It's a melancholy but profound truth. There are places in the cosmos we will never be able to visit, no matter how advanced our technology becomes. Not all stellar companions are stars. Some stars have brown dwarfs orbiting them, objects too small to be stars but too large to be planets. These brown dwarf companions were initially difficult to find because they're faint and don't emit much light, but improved observational techniques have revealed them orbiting various types of stars. There's an interesting gap called the brown dwarf desert, a scarcity of brown dwarfs orbiting close to Sun-like stars, while they're more common at larger distances. This desert may reflect how brown dwarfs and planets form differently, or how migration processes affect objects of different masses. Brown dwarf companions blur the line between stellar binaries and planetary systems, existing in a transitional category. Some brown dwarfs in binary systems show weather patterns, auroras, and other phenomena more commonly associated with planets, while others behave more like faint stars. They remind us that the universe creates objects across a continuous spectrum of masses, not just in neat categories. The Crab Nebula is one of the most studied objects in astronomy, a supernova remnant that resulted from an explosion observed by Chinese astronomers in 1054 CE. At its heart lies a pulsar, a rapidly spinning neutron star that rotates about 30 times per second. This pulsar powers the entire nebula, injecting energy that keeps the gas glowing nearly 1,000 years after the initial explosion. The pulsar's intense magnetic field and rapid rotation accelerate particles to high energies, creating a wind of charged particles that fills the nebula and causes it to emit light across the entire electromagnetic spectrum. The Crab Nebula is so bright and variable that it's used as a standard reference source for calibrating instruments. The pulsar itself is gradually slowing down, losing rotational energy that goes into powering the nebula. Eventually, millions of years from now, the pulsar will slow to the point where it can no longer energize the surrounding gas, and the nebula will fade, but for now, it remains one of the sky's most brilliant remnants of stellar death. While most asteroids are airless rocks, a few have been found to possess thin atmospheres or exospheres. The largest asteroid, Ceres, which is also classified as a dwarf planet, has a tenuous water vapor atmosphere that appears and disappears as sunlight sublimates ice from its surface. Other asteroids may have temporary atmospheres created by impacts that vaporize surface material. Some asteroids contain volatile materials that can outgas when heated by the sun, creating brief envelopes of gas around them. These atmospheres are nothing like Earth's. They're extremely thin, constantly escaping into space and often transient. But their existence shows that even small, seemingly inert bodies can have dynamic surfaces that interact with their space environment. Studying these thin atmospheres helps astronomers understand the composition of asteroids and the processes that affect small bodies in the solar system, bridging our understanding between planets with substantial atmospheres and completely airless worlds. We've wandered together through the phenomena of space, from auroras shimmering on distant planets to black holes spinning in the darkness, from newborn stars hidden in dusty clouds to ancient globular clusters drifting through galactic halos. We've seen how supernovae forge the elements of life, how galaxies collide and merge over billions of years, and how gravitational waves ripple through the fabric of spacetime itself. The universe is vast, mysterious, and endlessly fascinating. It pulses with energy, shimmers with light, and hums with invisible forces. From the smallest dust grain to the largest cosmic web, everything is connected, shaped by the same fundamental forces made from the same primordial matter. And you, resting here now, are part of that story too. The atoms in your body were born in stars. The rhythms of your breath echo the expansion and contraction of cosmic cycles. You are not separate from the universe. You are a way for the cosmos to know itself, to wonder, to dream. As your thoughts grow soft and your breathing deepens, let yourself float peacefully among the stars. The universe continues its slow unfolding, galaxies turning, stars shining, and phenomena beyond imagining playing out across the depths of space. There's nothing more you need to know tonight, nothing more you need to do. Just rest, drift, and let the quiet wonders of space carry you gently into sleep. Thank you for exploring these cosmic phenomena with me. I hope your dreams are filled with starlight and your rest is deep and peaceful. If you're still awake and would like to continue, there are more mysteries waiting. But if not, that's perfect too. Sleep well, dear traveler. Good night.